Okay, so we will begin with questions on the homework, section 1.3. Before we begin that, just need some comments. I mean, if you did it, no problem, but for now, and for most of the semester, ignore the following problems. If you got them, great. If you didn't, don't sweat it. 7, 9, 17, 19, 21, 31. Of these, 21 is actually a pretty important thing, but you won't fully understand that unless we went through 1.2, which we haven't completely. But as far as 7, 9, 17, all that stuff, it's something peculiar to this textbook more than linear algebra in general. I don't particularly see how it would be useful to us specifically. So other than that, if you have questions on any problem other than those, let's hear them. And we'll return to a problem like 21 after we complete section 1.2. Come in?
Can you do the 15?
What?
Can you do the 15?
15? Okay. What did 15 say?
Yeah, fine, thanks.
Okay. Tell me the matrix.
I don't have it on me.
It's the first part of it. It's one row, and it's K1, 1.
Okay.
And it's multiplied by another matrix, and it's a 3 by 3. And I'll say it by row. So on the top row is 1, 1, 0, 1, 0, 2, and then 0, 2, negative 3. And then you have one more matrix, and it's just a column, and it's K1, 1. And that's all equal to 0. Yep.
That's it?
Yep.
So we'll assume that this 0 is the 1 by 1 0. Won't see the difference between those. Okay, so who knows what to do here? Yeah, you just multiply them. Which ones do I multiply first?
First two.
Right. It actually doesn't matter, as we'll find soon. Matrix multiplication, it's not commutative, but it is associative. So it actually, if I have a triple, it doesn't matter if I multiply these two first or those two first, I'll get the same answer. But let's say, even if you didn't know that, whatever, whichever way you chose to multiply, it would work out. So let's just do the first two. How do I multiply this by that? First of all, what is the size of this matrix? 1 by 3, size of this, 3 by 3, size of this, 3 by 1. So when I multiply these two, what size should it be? It should be a what? It should be a 1 by 3. So I know that it's going to look like that times this. Okay, now what's the first element here? K times 1 plus 1 times 1 plus 1 by 0. Okay. Second element here. And the last element?
0 plus 1 by 2 plus 1 by minus 2.
Okay, so basically this guy is
K plus 1.
k plus 1,
K plus 2.
k plus 2,
Minus 1.
and minus 1. All of that times k1, 1 equals 0. Okay, so then what? Now I multiply again. What is the... So now this is a 1 by 3. This is a 3 by 1. And so we know our result should be a 1 by 1. Right? So what's the term going to look like? K squared plus k, because take this times that. Then k plus 2 times this. And minus 1. That should be 0. And so basically we have k squared plus 2k plus 1 equals 0, which means that k plus 1 squared must be 0. This means our k has no choice but to be minus 1. Other questions?
What is this with ignore? Are we ignoring those problems? I mean, we could
Yeah.
scratch it out of the homework after.
Yeah, you can forget about these essentially. 21 is pretty important. I recommend that you go back to that one after we cover 1.2. For this, you need 1.2.
So if you don't do those ones,
If you didn't do these ones, forget it. It's fine. You need 1.2 for 21 to fully grasp the answer. Any other questions? Yeah.
Could you go for 27?
27.
I think I got it, but like, I
What did
did
you
it
say?
like in like a guess and check, plug and chug kind of method and found the matrix, but I want to know like,
Okay, what's the...
so
How many 3x3 matrices can you find for which the
equation is satisfied for all choices of x, y, and z.
Okay, yeah, I don't remember something like that. Okay, so what, how did...
So it's 8
So
8
times the column matrix x, y, z.
X, Y, Z.
Yeah, equals the column matrix x plus y, x minus y, and 0.
Right, and we want to find, A is a 3x3, and we want to find how many possible ones there are, right? Okay. So, remember just like how in algebra class when you want to find something, you say let x equals whatever you want to find? In matrices, you can do sort of the same principle, or except it's not just one variable, you have each variable for an entry. So, for example, I would say here, let A be C, D, E, F, G, H, I, right? And the goal is to find what these numbers are, right? So if I'm looking for that, I call it a variable, right? I'm going to solve for these entries, right? So now I know that this times that should give me that, right? So A times X, Y, Z should give me A, B, C, D, E, F, G, H, I times X, Y, Z. That should be X plus Y, X minus Y, 0. This means, multiply these, what do I get?
ax plus by plus cz.
And then?
Dx y plus ey plus fc and gx hy plus iz.
Right? That matrix should be equal to this matrix. Okay. So, what must be the case? Matrix equality tells us that each corresponding entry must be the same, right? So it means that ax plus by plus cz must be equal to x plus y, right? Now if you have an equation with x, y, and z, you have another expression with x, y, z, another expression with x, y, and z, and you know they're equal, what must be true?
And the z terms in each is 0 because there's no z terms in the answer.
Almost. Well, the general idea is that the coefficients have to be the same. Right? The number of x's on this side must be the number of x's on that side and vice versa. There is no option. A cannot be anything other than 1, right? If I have 2x here, it's definitely not going to equal to x, right? So the coefficients must be the same. So basically right here, you do that equating coefficients method. So ax must be equal to x. This gives you that a must be 1. by must be equal to y. This also gives you that b must be 1. Cz must be equal to 0z, so that gives you c equals 0. Next row, do the same thing. D must be 1. E must be minus 1. F must be 0. So the last line. Everybody is 0 here. So G must be 0, H must be 0, I must be 0. Right? And we have no other option here if for equality. So this automatically gives me my matrix A. A has to be ABC, which is 1, 1, 0, DEF, which is 1 minus 1, 0, and GHI, which is 0, 0, 0. So there's only one matrix that would solve that equation. And one 3x3 matrix that will solve that equation, and that's it. Yes?
So we keep you all these terms of digits in the since the beginning.
Depends. In general, I'd like you to write out your steps. especially if they're very elementary. There are cases where it's just like, it's too much work to go through to solve something. And you can just spot an answer. The danger with this is when they say something like, find all 3x3 matrices that does something, inspection is probably not what you want to do, because you might spot one, but what if there are 2 or 3 or 4 or 5, right? You might not be able to spot all of them just by thinking and guessing and checking, right? So especially when they say, if they said, find any 3x3 matrix that does this, then sure, guess and check, you come up with one, great, right? But when they say find all, I'd be a lot more systematic with it, so that in case there are several possible solutions, I would actually pick it up by going through that process. So it depends on the question, sort of the situation, and how annoying it would actually be to solve something. Other questions?
So the matrix B is said to be a square matrix. B is equal to A.
Square root.
Okay.
Yeah, sorry, square root. Find 2 square roots of A if A is equal to 2.
Okay, so they basically give us a definition. B is the square root of the matrix A if BB equals A. And then they said find 2 square roots of A if
A is equal to 2 by 2 or 2.
Okay. So this is a 2 by 2, right? So this, by the way, means that B must be also a 2 by 2 matrix, right? Because that's the only thing that you can multiply by itself to get a 2 by 2 on the outside. The insides and the outside have to match up. B has to be a 2 by 2 matrix. So I'd set B to be very similar here, A, B, C, D. This general matrix that I'm going to find. So what I'm going to do now is I'm going to multiply both of them, set it equal to this guy, and try to find the solutions. Try to find at least 2, right? So A, B, C, D times A, B, C, D must be equal to 2, 2, 2, 2. This means, multiply this, what do I get? Over here. AB plus BD.
C plus
BC plus D squared. 2, 2, 2, 2. Now at this point, by the equalities of matrices, we can set up some equations here. A squared plus BC equals 2. AB plus BD equals 2. AC plus CD equals 2. BC plus D squared equals 2. Now this is a nonlinear system because we have squares. In general, they really suck to try and find an answer. So in this case, if I could eyeball it and try to figure out a couple solutions, I accept that as an answer. I only need to find 2, so if I can eyeball 2, that would be good. Right away, I'm adding 2 things. Knee-jerk reaction is 1 plus 1 equals 2. So clearly, if everyone's 1, that would work. And
-1.
if everyone's -1, that would also work. -1 times -1 is +1. -1 times -1 is +1. So A equals B equals C equals D all equal to 1, or A equals B equals C equals D all equal to -1. From this, I would do by inspection, and I'd accept that as an answer. So A would be either B would be either 1, 1, 1, 1, or B would be -1, -1, -1, -1. And that would be the answer.
And then for the next one, when they ask how many different ones do you find if the number is different, that's when you actually go through and find, like, go further with this equation?
Yeah,
Okay.
but we'll see. That's if you saw the inspection. I don't particularly like inspection methods because if you don't see it, then what? You know, what if I didn't see it? What would I have done? You know, Like it's good that you can see it, Jhevon. That's great. Like, what if I didn't see it? Like, how would you sort of tackle this system? Like, what do you think you could do?
Like implicitly, like take the second, the first and second, like how we used to do in linear algebra.
Yes. Well, we're in linear algebra now.
You know what I'm talking
So
about.
let's
Algebra.
we'll number these guys, right? So we can talk about them. So let's try to solve some of these guys. So first, elimination is a nice method to do. So I'm going to try to find something in common. Do we have any two equations with anything in common? 1 and 4, they both have a BC. So if I take 1 minus 4, what would I get? A squared minus d squared equals 0, which means that a squared equals d squared, which means that my a has to be plus or minus d. So I have two situations. Note, a is not equal to minus d. How do I know that? Because a is actually equal to minus d, and I look in equation 2, if I plug in minus d here, what would I get on the left side? 0, which is not equal to 2 last time I checked. Since equation 2 would give 0 equals 2, right? Which is crazy. So a must be equal to d, right? So whatever the value a is, it has to be the same as the value for d. Okay, what else can we say?
Plug that D into.
Yeah, let's plug that d into one of these, right? Then equation 2 would imply what? 2bd must be equal to 2, which means that b must be 1. And equation 3 would imply that 2cd must be 2, which means cd must be 1. Together these would imply that my b must be equal to c, right? By cancellation. So I know my a has to be the same as d and my b has to be the same as c. What else can I say now? So this gives me a chance to greatly reduce the number of variables I have, right? So I'm just going to replace them. Let's say I'm going to only use a and b as the variables, right? Because a also implies d and c also implies b. So let's rewrite these equations, right? So everywhere I see d, I'm going to replace with an a. Everywhere I see c, I'm going to replace with a b. What would happen to the first equation? I would get a squared plus
B squared.
b squared equals 2. Okay? Second equation would give me what?
I thought we were keeping A. We keeping A and B?
We're keeping a and b, yes.
Okay. So AB plus DA. So 2AB is equal to 2.
So you get 2ab equals 2, right? Or I can just say ab equals 1, right? That would come from equation 2. What would I get from equation 3?
AB plus
BD.
D.
You get exactly the same equation, right? I'd replace c with b, and I'd replace d with a. I would get 2ab equals 2. I get the same thing. Equation 3 would be the same thing. So no information from equation 3. What about equation 4?
C squared.
I would get b squared plus d I'm replacing with a.
So
A squared plus b squared, it will give me the same as the first equation. So I get no information from that. So both equation 1 and 4 tells me this, equation 2 and 3 tells me that. So now I've reduced my system. 2 equations, 2 unknowns. How do I get to those?
So equal to like A is equal to 1 over B plus variance for.
Sure. This means, this would say that a is equal to 1 over b. I can divide by b since it's definitely not 0. Because I take a product of two things and I don't get 0, and none of them are 0. So I would get a equals 1 over b, or vice versa, b equals 1 over a. So in equation this one, I would get a squared plus 1 over
A squared.
a squared equals 2. Multiply both sides by a squared, a to the 4th plus 1 equals 2a squared. This would mean that my a to the 4th minus 2a squared plus 1 equals 0. This would mean my a squared minus 1 squared equals 0. This means my a is equal to plus or minus 1. which means at the same time D is equal to plus or minus 1. At the same time, since B is 1 over A, that implies that B is equal to plus or minus 1. At the same time, since B is equal to C, that means that C is equal to plus or minus 1. And they all have the same signs at the same time. Hence, this is the answer. Other questions? You were saying about find all square roots of something.
No, the part B, they ask you how many different square, I think square roots or square something.
Square roots
Square
can you
root can you
find?
find? And they give you the next matrix. So I'm wondering, it's like, do we just continue this step and then we practically would find the answer?
Maybe. So if, what was the other matrix?
5, 0, 0,
5, 0, 0, 9? Ah, it's a diagonal matrix. There's a trick for those, but I didn't tell you about what those are yet, so let's, then we don't know them. Okay, what do we have? How many different square roots?
Oh yeah, how many different square roots can you find?
So same idea. I'd say my square root is a, b, c, d. I'd set up this equation, so this would be different here. Now inspection is kind of a little trickier because you'll never know. Did I actually find all of them, or is there an example that I'm not thinking of? So this one I definitely try to do it more systematically. So we have this guy must be equal to 5. This guy must be equal to 0. This guy must be equal to 0. This guy must be equal to 9. Okay, so what can we say now?
Then AB is equal to negative BD. And the same thing for negative 2.
AB is equal to what?
Negative BD, using the first two, like the, I'm sorry, the second and the third.
Okay.
The terms to the other side cancel out, and then the same thing, A is equal to D, negative D. A is equal to negative D again. So it's the same thing.
No, how do you get A equal to negative?
Because in the second and third one, it's equal to 0, so if you just move the BD term to the other side,
Okay.
divide both sides by B, you have A is equal to negative D for equation 2.
Okay,
A is equal to negative D again for equation 3.
but A could also be, yeah, you see, the thing with that is, that doesn't gel with these two. Because if I did the same idea here, I'd get a 4 on that side, you see that?
Yeah, that's something to work with.
I start jumping to conclusions. We have zeros to contend with here, so stop thinking the numbers are positive or negative. That might get you in trouble. If you see an equation with zeros, what is one thing that you'd always try to apply?
Then AB is equal to 0.
By writing it as a product, try to factor and see if you can get pieces equal to 0, right? This would imply what? B equals 0, or C would be equal to 0,
Or A.
or A plus D equals 0, right? Which is the one that you saw. A is equal to minus D. Now let's go through each case and see which ones make sense and which one gives us answers. If B equals 0, what can we say?
Then it's true, then AB.
Then, in the top, a squared, the first equation would give us that a squared is equal to 5, right? Which means that a is plus or minus radical 5. And we'd also get that d squared from equation 4. D squared would be 9, which means d must be equal to plus or minus 3. Could we say something about C? So if B is 0, I know what A is, I know what D is.
C would have to be 0.
C would have to be 0, right? Because I plug in numbers here for A and D and they're non-zero, but I'm getting multiplying by 0. C would have to also be 0. Okay, so right away here, my square roots could be plus or minus radical 5, 0, 0, plus or minus 3 in all orders, right? So that's 4 of them, right? There are four answers here. Right? I can be both positive, this negative, that positive, this negative, that negative, this positive, that negative, right? You get 4 answers of it. Are there any other ones, right? So this was if b equals 0, so we've done that case. What about if c equals 0? The same, right? Same. Right? What if a is equal to d? If a equals, so let's do the last case, a is equal to negative d, what's the consequence of that? So this is, if c equals 0, we get the same thing. If a equals minus d, what's the consequence of that?
It cannot be. Cannot be.
It cannot be, because 1 would tell us that a squared plus bc would equal to 5, but 4 would tell us, if I replace d with minus a, I get exactly the same equation on the right side, the same expression, but on this side it would be 9. So this is impossible. So we must have one of these two situations, in which case these are matrices. So B is radical 5, 0, 0, 3, or radical 5, 0, 0, minus 3, or minus radical 5, 0, 0, 3, or minus radical 5, 0, 0, minus 3. Those are the only possible square roots for this matrix. Is that all of 29?
No, there's a part C.
Yeah.
Imagine our disgust.
Does that always happen with the square matrix, like in this form? You always get the number squared? Or?
Yes. In fact, if D is any diagonal matrix, like A11, A22, up to ANN, and there are zeros everywhere else, then D raised to any power is actually, you just raise the elements on the diagonal to that power. But that's something that we'll find out later, right? So in other words, if you have a diagonal matrix, you want to take its square root, take the square root of each component.
Okay.
And so diagonal matrices will always have square roots, right? Remember, we're allowing complex numbers, so we can take square roots of negatives, so don't be afraid of that. We're working in F usually, remember, which can be real or complex. So a diagonal, for our purposes, will always have a square root,
Okay.
as long as the square root of the element is defined.
So that ties into part C, which is,
Part C says what?
are there any matrices that don't have square roots or something?
Every 2 by 2. Do you think every 2 by 2 matrix? Anybody know the rest of that?
Does every 2 by 2
At least one square root.
have at least one square root?
Explain your reasoning.
What do you think? Well, it seems to me here with the diagonal, this will pretty much work out the same no matter what numbers are here, right? So I know that every diagonal one should have one, so
Does it have to be real?
no.
I mean, if it was real, then for 2 by 2 matrices, the ones on the main diagonal entries, they have to be positive for the real numbers.
Yeah, but we don't care about that real.
Yeah.
So I think something like this will not give us what we want. So proving this in general will probably be annoying. So let's take those people on the main diagonal out of play. Let's say I'm looking at a matrix that's 0, 0. I'm trying to get a contradiction. So maybe if something is here and something is here, it won't work. Let's make our lives easier. If this doesn't work out, we try to build up. Let's take everyone but one guy out of play. And let's sort of see what happens. So sometimes you have to play around with these things. This is how it works.
But we can't prove everyone by one example.
No, I'm trying to disprove it.
Oh.
In which case you only have to find a contradiction.
In which case I have to find a single example. Because in general, if I wanted to prove it, it sort of means I'm going to have to tackle with this nonlinear system, which in general, it's going to be hard. So let's look at this guy. Does he have a square root? And maybe, if he does, then maybe we can get some sort of clue as to figuring out how we could actually prevent him from having a square root. What was the matrix here again, when I multiplied them?
BB is equal to A.
No, a squared plus blah, blah, blah.
Oh, it was, I didn't write it down.
You guys are getting too lazy because of the camera.
I have two of them. AB plus BD AC plus CD.
Okay, let's try to find this guy. A squared plus BC,
AB plus BD,
AB plus BD,
AC plus CD,
AC plus CD, BC plus D squared. Was that it?
yeah.
Okay, so that's 0, 1, 0, 0. Let's look at that guy. So I get my A squared plus BC equals 0. My AB plus BD equals 1. My AC plus CD equals 0. My BC plus D squared equals 0. Okay. From this one, either C equals 0 or A plus D equals 0, right? So this system, in this system, one of those two possibilities must be the case. Let's take one at a time. If C equals 0, what do we get? I get from equation 1, A must also be 0. No choice in the matter. If A is 0, then what?
Then B is equal to 1. Wait,
Then equation 2 would tell us what? BD is equal to 1. But equation 3 would tell us what? CD equals 0. In which case it doesn't really tell us anything about that guy. But we know where C equals 0. So from equation 4, I would get D equals 0, right? Which doesn't work in equation 3. Which doesn't work in equation 2. This contradicts that. Because my D was 0, then there's no way that could be 1. So this situation, impossible. No, we have another situation to worry about. What if my A plus D equals 0?
So wait, if you put one case, then you. Oh, okay.
No,
Gotcha,
it
gotcha,
can be
gotcha.
either or.
Gotcha.
There's another contradiction because C times.
No, equation 2 gives us a contradiction right away. If my A is equal to minus D, I get 0 equals 1. Ah, lucky, this has no square root. Right, so does every 2 by 2 matrix have a square root? No. Just found one that didn't.
So in general, do all matrices of that form that have zeros everywhere else and like a number in the top right corner have
As long as this number is non-zero, it shouldn't work.
right?
Because your second and fourth equation won't play nice together. So yeah, any number here except 0 won't work. Don't think we have much more time. Okay, we'll do that. Pass up the homework, and we'll try to rush through some more computational stuff. I'll send you the answers to the homework. But I can probably do that now. I think I should save it now. I did. Okay, great. You now have all the answers to the 1.3. So if I didn't get to your question, hopefully you can read the solution. Don't get it, fax me. In the tutoring center or something.
Are you there before 12?
Come again?
Are you there before 12?
No, I usually get there around. Last time we were in 1.1. 1.1 doesn't go into much. Last time we learned what? We can represent a system by a matrix equation. AX equals B, or an augmented matrix. It's called a matrix equation. This is called the augmented matrix for the system. Right? And we did a couple examples of writing a system in both of these forms. So now the question is, why do we care that we can write things in that form? Does it actually help us to solve anything? Turns out it does. It turns out, unlike nonlinear equations, there are pretty systematic ways to solve any linear equation, provided a solution even exists. And you'd be able to tell if a solution doesn't exist as well. And these guys go a long way. This is a very good system that we're going to be learning. In fact, your calculator, any computer that you ask it to solve a bunch of linear systems, this is sort of the method that it's going to use. Well, the one we're going to see in 1.2. Right? So you type in Wolfram alpha, solve this system of equations for me. Wolfram alpha does this, what we're going to be doing in 1.2, right? Which is called Gaussian elimination. Let's sort of lead into, let's sort of build up to that with an example. I don't know if I wrote this. Consider a system. X plus y equals 3. X minus y equals minus 1. Okay, pretend we're back in algebra class. How would you solve this?
Just add them together.
You could just add them together. Okay? I'm going to say something that might be like, why would you even think of that? But I'll bring it back to why we would even think of that. Note, it would not make a difference if I labeled 1, 2, and 2, 1, would it? It wouldn't make a difference, right? I call this equation 1 versus that equation 1. It doesn't matter, right? We're going to talk about why we even care about that fact, right? It seems trivial, but it's actually an important fact. It'll be important in hindsight. So really, it doesn't matter who I label what. I can switch this guy and make him row 1, or I can make this guy row 1. Doesn't matter. It's not going to change the answer. Note also, This is another elementary fact that we often take for granted. To multiply both sides of an equation by a non-zero number. Right? I can multiply both sides of an equation by any number I want. That's not zero. It's not going to change the solutions. We'll bring that back. But let's actually try to solve this. What can I do? I said add them, right? I can get 2x equals 2, and what I did was I added equation 1 and equation 2. From this I can get x equals 1, right? And then I can plug that in and say 1 minus y is equal to minus 1. This means that my y must be what? 2. Okay, good way to get a solution. Okay. All right, great. So we went back to college algebra. So what? Let's do another example, because I'm going to sort of tie this into what we're going to be doing now. What if I had x plus 2y equals 7, and I have 3x plus minus y equals 7? Call this equation 1, call this equation 2. Solve.
The bottom equation by 2.
I could multiply the bottom equation by 2, which will not change the answer. Okay? So I can rewrite, do nothing to this guy, but the bottom one, I'm going to multiply by a 2. I would get 6x minus 2y equals 14. This is equation 2 times 2. At this point, what can I do? I can add them. I would get 7x equals 21, right? And this, call this in row 3, by adding 1 and 3, right? From this I can get to my answer. X would be 3. Then I'd be able to say what y is, right? 3 plus 2 times y must be 7, which means that y must be 2, right? Okay. Now, okay, Jhevon, why did we walk down memory lane, and why did you show us this? If an augmented matrix represents a system, it stands to reason that anything I can do with a system of equations, I should be able to do with an augmented matrix, because they're the same thing, right? It's just a different way, all different names for the same thing, right? How would I write that system, that last one, as an augmented matrix? 1, 2, 7. That's an augmented matrix. Okay, let's try to mimic what we did over here with the augmented matrix. Right? Here's my row 1, here's my row 2. What was the first thing I did?
Multiply 1 by minus 3 plus the second one.
Take it one step at a time. The first row, no, equation 1, at first I didn't do anything, right? I just left it there, 1, 2, 7. So I just recopied row 1. Row 2 I actually changed. Row 2, I got a 6, a minus 2, and a 14. Now this was actually row 2 times 2, right? That would be the second thing that I did, right? Just breaking it down into very elementary steps. What did I do next? I added things, right? How did I do that? So I could replace any one of these equations, it won't make a difference. We can replace the uglier one just because. You'll see that it won't make any difference later on. So I developed a brand new equation by adding these two, right? I took row 1 plus the new row 2 that I made from the previous step. Row 2 from previous step. And what was the resulting equation? So that would be a 7x and 0y's and 21. Now remember, this column here represents the variables coefficients of x, that represents the variable coefficients of y. Now when I get to this position, something magical happened. I could easily figure out the solution to one of these variables, right? All I did was now I transformed this back into equation land. This tells me that 7x equals 21, which means that my x equals 3, which means that my y equals 2. Right? So I made an augmented matrix, did a bunch of steps. These steps resulted in a row in the matrix that I could transform to an equation where it's easy to solve for one of my variables. I did it in such a way that I eliminated one of these variables. Notice I could have gone further. I could have taken an extra step if I wanted to. In this last line, I could have divided through by 7, right? Because I could do that in equation, I could do that to my matrix. And this is an even nicer equation. I could say right away, x equals 3 is that solution. I wouldn't even have to go to equation land. I get the answer right away, right? Now there's nothing special about this particular example. I could have done this with literally any 2x2 system and try to figure out an answer. What we did are the steps we took. Are called elementary row operations. They mimic things we can do to equations in the most basic sense. They mimic basic things we can do to equations to get to a nicer answer where we can get solutions. And I actually hinted to these before. There are 3 elementary row operations. Right? There are 3 basic things we can do to any equation that won't change the solution but can transform the equation into something a lot nicer to deal with. They have names. We call one a type 1 row operation. See why this is important later. It's the one that was kind of trivial where you're like, why do we have to even know that? This says we can switch 2 rows. Right? This is called a type 1 row operation. It doesn't matter if I call this one equation 1 and that equation 2 or vice versa. I can think of any one as being above the other. I can switch 2 rows, it actually won't change my solutions. This won't change the solution. It seems like something that's quite trivial, but by 1.2 you'll see why something like this is really nice. Right? Being able to say I can do that. I can label equations however I want. Type 2 has a bit more oomph. That's the first step I took here. Type 2 row operation. This says we can multiply a row, right? Remember, each row represents an equation. I can multiply an equation by a non-zero constant on both sides. It says I can multiply a row by a non-zero constant. This will not change the solution. It only helps to put it in a more convenient form. Right? So one basic thing I can do with rows in an augmented matrix, I can switch them around, and I can multiply any row I want by a non-zero constant. It won't change my answers, but it gets things to a more convenient one. The next one is what we did with process of elimination. This is called a type 3 row operation. This is what we did when I multiplied one row by 2 and then I added it to the other row, right? This is what I did. Replace a row by itself plus a multiple of another row. And again, this does not change our solution. This is literally the process of elimination, described in an elementary mathematical operation. And that basically ends 1.1. They left us in suspense. That's all they left us with. Okay, so there's these cool things called row operations that we can do in augmented matrices. Bye. How do I systematize this? How do I program a computer to do this? Right? That's the question. Okay, there are these things called row operations. I see why they make sense, because they make sense with equations, and our augmented matrix represents equations. Okay, you sold me. How do I use this? How do I put this in a system where I can solve any linear equation I want? Any system of linear equations I want, or find the solution. This leads us to 1.2, and the process is called Gaussian elimination. AKA Gauss-Jordan elimination. Gauss and Jordan were two mathematicians. Gauss is a very famous mathematician. All mathematicians talk about him in awe, half God, half man kind of thing. Yeah, he's the kind of guy doing calculus at 4 years old and blah, blah, blah. Right? You hear about those kind of guys, he was actually such a guy. Probably a handful of such kind of people in history. That sort of thing is not as common as you might think. So, Gaussian elimination, right? Basically what this is, uses row operations to put augmented matrices in a convenient form. Convenient form means a form by which it's easy for me to find solutions, right? But us being mathematicians, that definition is way too vague. What is a convenient form? How do you define a convenient form, right? I can't program a computer, put this in a convenient form. Okay. What is a convenient form? We have to come up with a definition that I can put in a program, computer, do this. If you hit here, this is called a convenient form, right? These forms have names. There are two convenient forms. One is called row echelon form. I do not know where the name came from. That's what it's called. Row echelon form is one of the convenient forms. Two, it's called reduced row echelon form, which is row echelon form on steroids, right? Basically the difference between a row echelon form and a reduced row echelon form, well, I actually never showed you a reduced row echelon form. But it takes that extra step. Remember there was a point here where I could get to an answer, but I could have actually gone a step further and get to a nicer point. That's sort of the difference between a row echelon form. It's good enough, But this is even better, right? It's easier to copy solutions. And we're going to define exactly what these are. Reduced row echelon form. This is called REF. I might abbreviate that. And this is, of course, called RREF. These abbreviations are pretty much universal. You see those abbreviations in a linear algebra textbook. This is what they're talking about. So I'll probably just jump in and define these for you, and then I'll show you why these forms are considered convenient. So let me make sure I have the exact definition, not missing anything. Let's deal with row echelon form. An augmented matrix is said to be in row echelon form if a few things happen. One, any 0 rows are moved to the bottom. I can do that. That's a type 1 operation. It won't change my solution to just say, if you're all zeros, go to the bottom. Right? So you don't have to have a 0 row, but if a 0 exists, put it at the bottom. This is the first step in a row, a convenient form, a row echelon form. The first non-zero number in any row must be a 1. Nothing super spectacular about that requirement, but makes it easier for a computer to tell you the answer right away without you having to do any extra work. Why? Because that means that the coefficient of the leading variable is 1. So you just have x. You can move everything over and right away say x equals this. Right? You don't have to say 2x equals this, then an extra step to divide by 2. The computer is going to do all that for you. Okay? So first number non-zero in any row, first non-zero number in any row must be a 1. This one is called a pivot or leading 1. I think your book uses the term leading 1 all the time. Other textbooks would use the word pivot, and by habit I might use the word pivot because another textbook I taught linear algebra from used the word pivot. I got used to saying pivot. Okay, so it's called a pivot or a leading 1. 3. Each pivot is to the left of the pivot above it. The pivots in the rows above it. Except obviously if you're in the top row, there's no one above you. And 4, in any column with a pivot, in any column with a pivot, there are zeros in all entries below the pivot. except perhaps, of course, in the last row, obvious detail. This form is called row echelon form. Did I miss anything? Nope. Reducer echelon form goes one step further. One requirement which by hand can be a pain to get to, but a computer will have no trouble getting to it. If I add the condition that I want zeros also above each pivot, not in the top row, that puts me in what we call reduced echelon form. It means once I can solve for a variable, that variable will not appear in any other equation that I need to solve for it again, right? That makes it slightly redundant. Right? So once I can use one equation and say x equals this, I will never have x equals anything anywhere else, right? I can just not worry about x once I found the x. I don't want to worry about the x anymore, right? So that's called reducer echelon form. That's it. So we don't have time to demonstrate how to put something in these forms yet. We'll do that next time, which I believe our next class is Wednesday. Is that correct?
Yeah.
But for now, I just want to list a bunch of matrices, and you tell me if they're in reducer echelon form or not, and then we'll get out of here. Right? Row echelon form or reduced row echelon form? That is the question of the day. Here are the matrices. 1, 2, 0, 1. 1, 0, 7, 5, 0, 1, 2, 3. 0, 0, 0, 0, 0, 0, 0, 0. 1, 0, 2, 3. 1, 0, 4, 7. 0, 0, 1, 3. 1, 0, 2, 3. 0, 1, 0, 4. 0, 0, 1, 7. So you're going to tell me, is it in reducer echelon form, row echelon form, or neither is going to be, is the question here. Just want to see if you can recognize the form, right? If you're a computer, could you tell when you're in a convenient form? Two more. You guys can start figuring out the first few so that we can run through them quickly. So on the first one. It's in row echelon form. right? There are no non-zero, there are no all zero rows. The first number in the first row is a 1, the first non-zero number in the second row, as you're moving from left to right, obviously, left to right, is also a 1. The pivot in the second row is to the, did I say left before?
Yeah.
I meant right.
Yeah.
Change that left to right. Probably put an annotation here. It's to the right of the guy above it. So this is in row echelon form. This guy, this is actually reduced row echelon form. Right? First non-zero number in any zero row is a 1. All zero rows are at the bottom. Pivot in the second row is to the right of the pivot in the top row. The pivot in the top row has zeros all the way underneath. The pivot in the 1 has all zeros underneath and zeros above. This is reduced row echelon form. This is neither. What's the problem?
You're not getting the first column.
First column, that 1 shouldn't be there, right? He's not to the right of the guy above him. Row echelon
I'm
form.
not sure what you wrote. You said each pivot is to the left of the one above it.
To the right.
You didn't
It should
say
be to the right. Change left. Where I said each pivot is to the left of the one above it.
Isn't that correct?
No, to the right. I think in my notes I wrote it to the left of the one below
If
it.
it's coming from the bottom, then wouldn't it be on the...
No, this is to the right of that guy.
But you said from... Okay, never mind.
It should be right. The way I phrase it is right. Oh man, there are way too many puns. This is a reduced row echelon form. Why is it not reduced?
Because the two.
That 2, right? Above this pivot, there is not all zeros.
Neither,
Why neither?
because we have 2 and the second.
Because this, the first non-zero number in the second row is not a 1. This is neither.
Neither, because the second row is zeros.
This is neither.
You need to change the zeros.
Because this whole row here is a 0 row and it's not at the bottom.
Reduced.
Yeah.
This is reduced row echelon form. Has all the characteristics. First non-zero number is a 1, zeros at the bottom. Pivots have zeros above and below. Pivot in the second row is to the right of the pivot in the top row.
Row echelon form.
This is row echelon form. Right? First non-zero number in any row is a 1. Pivots here are to the right of all guys above them. Zeros below all pivots. There are no zeros on top of them, so it's not reduced for that reason. Right?
Quick announcement, if anyone needs the PDF of the textbook, let you know about.
So, yeah, so 1.1 we finished, so homework for that is due on Wednesday. 1.2 we have not done. Next time I will show you why these forms are very convenient and how we can use them to solve systems. So we'll stop there. And you guys have the solutions, the answers for 1.3 in your email.